Okay, so last time we ended with this situation here where we said that what matters most when trying to judge how good or bad a score is involves comparing it with the average score in the whole group. Okay, so how far above average or below average we are. But we also need to take into account how spread the numbers are. So being far away from the average has a much bigger meaning if everybody else is generally clumped around the average. So to measure this precisely, we were after a way to pinpoint exactly where we are on these curves, these normal distributions. And that's what we'll try and work towards in this video. So let's bring up a generic normal distribution here. We said that such a curve has two main ingredients: the center, which corresponds to the peak of the curve, the number that most of the scores are somewhat close to. And that number is given by the mean, the average. As a side note, because we assume symmetry here, this number will also be the median, but in any case, that number goes down here on the number line. Then we also have the spread, which we measure by using the standard deviation. Now, if you've forgotten what that is, I'll leave a link in the description, but in short, the standard deviation measures spread by sort of averaging how far everyone is from the mean. And we use that symbol sigma to denote that number. So we want a way to visualize what this standard deviation does, and actually along the way we'll tackle our main problem, which, remember, was to be able to use numbers to pinpoint the position of any score on this curve. What we're going to do is mark out several positions like this, where the width of each section or the size of each step is exactly the standard deviation. So of course these steps are all equally spaced, they will all be given by the standard deviation. Now, why would this sort of setup be helpful? It's because if the spread is narrower, then the standard deviation shrinks accordingly, and that allows those red markers to continue tracking the same relative positions on the curve, which is what we were after all along. Likewise, if the spread is super wide, the standard deviation will increase accordingly, and those red markers, again, are still tracking the same relative positions on the curve. So now that we know these red position markers do the job perfectly, we can easily attach numbers to them, and the most natural way to do that is this. We put the number 0 above the average. Okay, so if you get a score of 0, that means you're dead average, right? Then going one whole step, so one whole standard deviation above average, brings us to the next marker, which will give the number 1. Going another standard deviation across takes us to the next marker, which we'll say is number 2. Then similar for number 3. Okay, there's actually been a red marker there this whole time, but he's a bit too short to see unless you're really looking out for him. And it'll be the same thing going the other way, but now because we're looking at scores below average, we give them negative numbers. So this position here gets the number -1. Then going another step to the left, we get -2. Then similar for -3. And again, what makes these green scores so helpful is that they mark positions on the curve in such a way that they keep their relative position as the spread of the scores might get wider like that, or maybe narrower like this, right? These green scores take that spread into account and keep the same relative positions, which is what we really wanted from last time. So these green scores are what we call Z-scores, or sometimes standardized scores. And to give a simple description of what they do, they tell you your position on the bell curve, on the normal distribution, by counting the number of standard deviations above average you are. So as we've been saying, we can pinpoint exact positions on the curve by taking equal steps along the number line where each step is a standard deviation. Then the Z-score is just the number of steps above average you are. So if you're dead on average, your Z-score will be 0. If you're above average, your Z-score will be positive. And if you're below average, your Z-score is going to be negative. And this topic pretty much revolves around this one definition, okay? A score called the z-score or the standardized score that counts the number of standard deviations above average you are. And this score does the job of pinpointing where you are on the normal distribution. So let's finish with a simple example here. We have a test with normally distributed scores with a mean of 60 and a standard deviation of 8. What I often recommend is actually drawing the picture we've been building, okay? It just tends to make things easier when you can see everything in front of you. So we draw the curve first. Then we would put the different position markers with the z-scores on top like that. Pretty much every picture will look like this up to this point. But now to make it fit this particular story, we first need to indicate this mean of 60, which means the blue line, the peak of the bell curve, corresponds to a score of 60 there. Then the standard deviation is 8, which means that we're taking steps of 8 across. So the score at the green 1 must be 68. Then we have 76, that's just 68 plus 8. Then we have 84, that's 76 plus 8. Then we can go the other way, meaning we go back by 8. So 60 minus 8 is 52. Minus 8 again, that's 44. Then one more time for fun, that's 36. Now, will we use all of these numbers? Well, almost never, okay? But again, I just find it helps to have as much of the story as possible laid out in front of us, especially if the question is a bit harder, okay? All right, so actually answering part A could almost be immediate, right? For the raw mark corresponding to a z-score of 2, we can just look at the score corresponding to the green 2 on our curve. And so the answer is just 76, right? But just to hammer in how we got there, and really if you didn't want to draw the picture at the start, right, we can confirm this with just the given information in the question, right? We start from the mean of 60. Then what does the z-score of 2 do? Well, it means we are 2 standard deviations above average. So from this average of 60, we need to go forward 2 steps, where each step is the standard deviation of 8. So from the average of 60, we would go forward by 2 steps of 8. And you can confirm that also gives 76. Okay, so working out a raw mark from a z-score is quite immediate from just the story itself, right? We start on the average, then the z-score tells us how many standard deviations we need to go forwards or backwards by. Then what about part B? We want to know the z-score, so the green number, corresponding to a raw mark of 38. Now 38 isn't a score we've written down, so it's going to be some kind of decimal, right? On the number line, it's round about here, okay? So first, how far away from the average is that? We can subtract to see, so 38 minus 60. And we get negative 22. Note the negative makes perfect sense because our score is below average, so we're looking at a negative z-score here. But the z-score isn't this negative 22 number. The z-score is counting in steps of 8 because it's counting the number of standard deviations, which in this story is 8. So back on the picture, we're thinking in these steps here, where the last one isn't one full step, right? We know the answer is negative 2 point something, okay? But to know exactly, we're really asking how many 8s make up negative 22. So to see that, we can just divide them. And we get negative 2.75, which from the picture was totally expected. So if we need to work out a z-score, we just start by seeing exactly how far from the average we are, and then we can just divide by the standard deviation to see how many of those steps we're taking, and that's what gives us the z-score. So that's all for this one. Thanks for watching. See you around.